Picture a satellite view of the North Atlantic in the middle of August 2026. Over one stretch of ocean, clouds curve into a long, sweeping arc reaching north toward Iceland and the edge of Greenland. Farther south, over the Iberian Peninsula and Central Europe, the sky is almost empty. Not a single significant cloud front for hundreds of miles. Underneath that open sky, the air has been sitting still over the land for days. Farther south still, the Mediterranean is warm enough that its temperature has become a subject of conversation among oceanographers in its own right, though that particular story has been building for months, on a much slower clock than anything happening in the sky above it. Three very different scenes, separated by only a few hundred miles of latitude. And at least two of them, the cloud arc to the north and the stillness to the south, are almost certainly connected by the same current of moving air far overhead. That current has no name most people would recognize on sight, and almost nobody has ever seen it directly. It exists high above us, at the altitude where passenger jets cruise, and it has no fixed beginning, no fixed end, and no permanent shape. Sometimes it runs in something close to a straight line, circling the hemisphere at speed. Other times it bends into enormous loops, and when that happens, the weather underneath stops moving on schedule. It lingers. A heat wave that should last 2 days stretches into 2 weeks. Rain that should pass through in an afternoon keeps returning to the same towns, the same fields, the same rivers. That current is the jet stream, and the question at the center of this film is simple to ask and much harder to answer. Why does a river of air, 7 or 8 miles above our heads, sometimes bend so sharply? And how does that bending decide how long a single stretch of weather stays put over a single stretch of ground? The summer of 2026 in Europe was one of the most talked about in years. Seasonal outlooks from the World Meteorological Organization and the Copernicus Climate Change Service had already pointed, early in the season, toward a higher-than-normal chance of above-average temperatures across most of the continent, and that expectation held. Heat waves kept returning, one after another, rather than arriving once and moving on. By the middle of August, climatologists were tracking yet another one, and its immediate cause, according to assessments from the European Center for Medium-Range Weather Forecasts and Copernicus, looked familiar. A stubborn ridge of high pressure, wedged between 2 areas of lower pressure. But it would be an oversimplification to say that one unchanging configuration of the jet stream sat over Europe for the entire summer. Each new heat wave built up under its own conditions, echoing a pattern that had shown up before without being a literal continuation of it. Separately, marine monitoring services were reporting that unusually warm water in the western Mediterranean and the northeastern Atlantic had persisted through most of the summer, a process running on its own, far more sluggish timescale, one that the ocean and the atmosphere sustained together without reducing to a single overhead pattern. Taken together, they point to a summer in which parts of Europe repeatedly experienced slowly evolving large-scale weather patterns, episodes that kept returning without ever quite behaving like a single, unbroken stretch. To understand why the atmosphere is even capable of getting stuck like this, we need to climb well above the clouds, to where this story actually begins. At around 10 kilometers, roughly 33,000 feet, where transatlantic flights cruise, the air does not behave the way most people imagine wind behaving. There is no pipe with solid walls up there, no tunnel funneling air the way water runs through a channel. What exists instead is a comparatively narrow region where the wind is considerably stronger than in the layers around it, a kind of concentrated current inside the broader west-to-east flow that dominates the middle latitudes. For our part of the world, the one that matters most is the polar front jet stream, which marks the boundary where cold polar air meets warmer mid-latitude air. That boundary can shift enormously. Sometimes it passes south of the British Isles. Sometimes it retreats far north toward Scandinavia. Its wind speed is just as variable, changing with the season, with the strength of the temperature contrast on any given day, and with how active the broader circulation happens to be. There is no single number you could point to and call the jet stream speed once and for all, because this current is alive in a sense. It breathes. It changes almost daily. To understand where wind this strong even comes from, we have to go back to one of the most basic facts about our planet. The sun does not heat Earth evenly. The equator receives far more energy than the poles, simply because sunlight strikes it more directly. That creates a lasting temperature contrast between the tropics and the polar regions. It's tempting to say that warm air from the south simply collides with cold air from the north, and that collision produces wind. But that explanation is too crude and not really accurate. What actually happens is that the temperature contrast changes how quickly pressure drops with altitude at different latitudes. Above warmer air, pressure falls off more slowly with height. Above colder air, it falls off faster. That difference produces a horizontal pressure gradient in the upper atmosphere, one that grows stronger the higher you go. Meteorologists call the link between a horizontal temperature gradient and increasing wind with altitude the thermal wind relationship. And it's this relationship that explains why the strongest winds on the planet aren't found at the surface, but far above it, near the top of the troposphere. A temperature contrast on its own isn't enough to produce a narrow, fast current stretched out along a line of latitude, though. For that, Earth's rotation has to enter the picture. Because the planet spins, anything moving through the atmosphere, a parcel of air, an aircraft, a developing storm, gets deflected away from a straight-line path. That deflection is known as the Coriolis effect, and it's worth being precise about what it actually does. It doesn't create wind. It isn't a source of energy in its own right. What it does is change the direction of air that has already been set in motion by a pressure difference. As a result, air that would otherwise simply flow from high pressure toward low pressure ends up curving so strongly that it moves almost parallel to the lines of equal pressure rather than across them. It's the combination of the temperature gradient, the way pressure changes with height, and the planet's rotation that together produce what we call the jet stream, a narrow, fast corridor of concentrated westerly wind riding high above the surface of the Earth. There's a common misconception worth clearing up right away. The jet stream isn't a fixed object that either exists in some unchanging state or suddenly breaks. It's constantly drifting north and south, speeding up and slowing down, occasionally splitting into two separate branches before merging again into one. It tends to strengthen in winter, when the temperature contrast between the tropics and the pole is at its greatest, and weaken in summer, when that contrast narrows. All of this is ordinary, everyday atmospheric behavior, not some exception to the rule. The real story doesn't begin when the jet stream changes. It begins when the shape of that change becomes extreme. When a flow that's broadly west to east starts bending so sharply that it forms a chain of enormous loops. Which brings us to one of the central ideas of this whole film: Rossby waves. They're named after the Swedish-American meteorologist Carl Gustav Rossby, who worked out mathematically, back in the 1930s, why large-scale airflow in the middle latitudes tends to meander rather than run in a straight line. The cause, again, comes back to the planet's rotation, but this time to how the strength of that deflecting effect changes with latitude. It's stronger closer to the poles and weaker closer to the equator. When a large mass of air shifts north or south from where it started, that difference pulls it back. But momentum carries it past its original position and it curves the other way. The result is a wave motion stretched across thousands of miles, the atmosphere quite literally oscillating along a line of latitude, like some enormous vibrating string. You don't need to dive into the mathematics of vorticity to grasp the essential point. The planet's spin doesn't act with equal strength everywhere, and that inequality forces the large-scale flow in the upper troposphere to travel not in a straight line, but along a winding path. On maps of the upper atmosphere, these waves show up as an alternating series of bulges and dips. A section where the flow bends northward is called a ridge. It often brings warmer air farther poleward than usual. A section where the flow bends southward is called a trough, and it typically lets colder air push farther toward the equator than it otherwise would. But here's an important caution. A ridge is not automatically synonymous with a heat wave, and a trough is not automatically synonymous with a downpour. Actual weather at the surface depends on a long list of additional factors: humidity, the condition of the soil, proximity to the sea, the time of year, and how deep and stable the wave itself is. A ridge creates conditions favorable for warming without guaranteeing extreme heat. In the same way, a trough creates conditions favorable for rain without guaranteeing a flood. One of the more interesting and less obvious ideas in this story is the difference between the motion of the air itself and the motion of the wave pattern that air is moving through. Inside the jet stream, individual air parcels can race along at enormous speed, crossing half an ocean in a matter of hours. But the shape of the wave, the position of a ridge here, a trough there, can stay almost unchanged for days at a time. It's a bit like a wave moving across the surface of open water. The pattern travels along the surface, but any single drop of water mostly just rises and falls in place rather than traveling with the wave from one end to the other. That distinction between fast-moving air and a slow-moving, large-scale pattern explains one of the more counterintuitive facts about the atmosphere. The current far overhead can be moving incredibly fast, while the weather underneath barely changes for days on end. So why does weather get stuck in the first place? When the large-scale wave pattern, that sequence of ridges and troughs, slows down, an area of high pressure sitting beneath a ridge can hold its position over the same region long enough to produce an extended stretch of dry, hot weather. And in reverse, if a slow-moving trough keeps feeding moist air upward and inward, wet weather can settle in for an unusually long stretch too. It's important to be precise here. This doesn't mean the jet stream has stopped. That would be a crude and inaccurate way to put it. The current keeps existing and keeps moving air. What's really happening is that the large-scale configuration it's organized into has temporarily stopped making efficient progress toward the east. Meteorologists have a name for this scenario: atmospheric blocking. It's a distinct mechanism in its own right, not to be confused with the jet stream itself or with Rossby waves as a general phenomenon. Blocking is a specific, stable pressure configuration that interrupts the usual west-to-east progression of weather systems. One of the more recognizable types is what's known as an omega block, named because the pattern on a map of upper-level heights can resemble the shape of the Greek letter omega, a region of high pressure in the center, flanked by two areas of lower pressure on either side. But it's worth resisting the temptation to turn that resemblance into a strict rule. Not every ridge that looks vaguely like this shape qualifies, in a strict meteorological sense, as a fully developed persistent block. For a configuration to earn that label, it has to hold its shape for several days running, genuinely disrupting the normal flow of weather systems rather than briefly resembling that shape once. Why can a pattern like this hold on for so long? The answer has to do with the fact that atmospheric waves don't exist in isolation. They're constantly interacting with each other, exchanging energy and momentum, and interacting with the cyclones developing and moving nearby. How long a block survives often depends on what's happening in the flow far upstream and downstream of it. What's unfolding over the Pacific or North America can determine whether a block over Europe holds for several more days or starts breaking down tomorrow. You don't need to go deep into dynamical meteorology to grasp the main idea. A stable block doesn't hold together on its own. It holds together because the entire large-scale circulation at that moment happens to favor its existence. When a ridge of high pressure settles over a region for an extended period, a whole chain of processes kicks in that can intensify the heat. Air beneath such a ridge tends to sink, and sinking air compresses and warms. At the same time, cloud cover thins out, because that sinking motion suppresses the formation of clouds, which means more solar radiation reaches the ground. The soil warms, moisture gradually evaporates from it, and a further reinforcing mechanism switches on: the feedback between soil moisture and air temperature. As long as there's enough moisture in the ground, a large share of incoming solar energy goes toward evaporating that moisture rather than directly heating the surface. But once the soil dries out, there's nothing left to evaporate, and nearly all of that energy goes into heating instead. So the air above dry ground warms noticeably faster than it does above moist ground. That's why a prolonged heat wave so often comes hand in hand with accelerating soil drying. And the longer a ridge holds its position, the more that feedback loop can spin up. The opposite situation unfolds when it's not a ridge but a slow-moving trough, or the cyclonic system tied to it that lingers over a region. That sets up conditions favorable for sustained rising air, cloud formation, and repeated, sometimes prolonged, rainfall. But caution matters here too. Not every block automatically means flooding somewhere nearby. A great deal depends on how much moisture is genuinely available to the system, how vigorously the air is rising, and how long the configuration itself holds together. Perhaps the clearest evidence that we're not dealing with a random collection of local quirks, but with one connected system, is the fact that a single large-scale wave configuration can support very different weather in different places at the same time. A ridge over one part of a continent might bring a prolonged heat wave, while a neighboring trough over another part brings extended rain and relative cool. And a third region caught in between might avoid both extremes simply because of where it sits. These aren't three unrelated coincidences. They can be different regional expressions of different parts of the same large-scale wave pattern, each one shaped by whichever part of that wave happens to sit overhead at the time. The North Atlantic holds a special place in this picture. It's where a substantial share of the cyclones that go on to shape the weather of Western and Central Europe are born and develop. The jet stream plays an important role in steering what's known as the storm track, the general path along which these cyclones tend to travel from west to east. But it would be misleading to describe that relationship as one-directional, as though the jet stream simply pushes cyclones along like a conveyor belt. In reality, the connection runs both ways. As cyclones develop and release energy, they can redistribute momentum through the atmosphere and noticeably reshape the position and structure of the jet stream itself. It's a dynamic, two-way interaction, not a simple hierarchy in which the flow commands and the storms obey. This fast-moving current has a very down-to-earth practical relevance too, for aviation. Aircraft flying in the same direction as the jet stream can pick up a substantial tailwind and shave real time off a transatlantic crossing, while aircraft flying against it can lose that same time to a stubborn headwind. Air traffic controllers and pilots routinely factor the jet stream's current position and strength into flight planning. The same phenomenon is sometimes linked to clear air turbulence, the sudden jolt a plane can experience in the absence of any visible cloud or storm. The usual cause is strong wind shear, a sharp change in wind speed or direction within a narrow layer of the atmosphere. And shear like that shows up especially often near the edges of the jet stream. But it would be wrong to say that all turbulence of this kind comes from the jet stream alone. It's one elevated risk zone among several, not the only source of that kind of jolt. Now we arrive at the most sensitive and most actively debated part of this story, the role of the Arctic. This is where maximum scientific care is essential, because it's exactly where popular explanations tend to drift furthest from what the research actually shows. That the Arctic is warming faster than the planet as a whole is well established, confirmed by decades of observation. It's known as Arctic amplification. Several processes contribute to it. Melting sea ice lowers the surface's reflectivity, so the ocean absorbs more solar energy. The pattern of heat exchange between ocean and atmosphere shifts, and other processes tied to how energy is redistributed at high latitudes play a role as well. The next step in the reasoning, though, is considerably more complicated than it's often made to sound. The popular version goes something like this. The Arctic warms faster than the middle latitudes, so the temperature contrast between the pole and the tropics shrinks, so the jet stream weakens, becomes more wavy, and grows more prone to blocking. Every link in that chain is scientifically interesting, but presenting the whole thing as an established universal law would be premature. Large multi-model research does support one part of it fairly robustly. The loss of Arctic sea ice appears to push the main axis of the North Atlantic jet stream closer to the equator, a result that holds up consistently across different models. But the further claim that Arctic amplification specifically makes the flow more wavy and systematically increases blocking remains a hypothesis rather than an accepted conclusion. It has real scientific support, first proposed over a decade ago, and it continues to be actively debated. More recent analysis has even pointed to something closer to the opposite in places. Sea ice loss reducing waviness at certain stages rather than increasing it, suggesting that other factors are likely doing much of the work behind the changes researchers actually observe. So why does the science remain unsettled if the Arctic really is warming? Because the Arctic is far from the only influence on the jet stream's shape and behavior. What matters also includes the temperature of the tropical upper atmosphere, temperature gradients across different latitudes higher up, processes in the stratosphere, ocean conditions in very different parts of the world, snow cover across the continents, the atmosphere's own internal variability, which has always existed independent of any climate trend, the position of the storm tracks, and the season. These factors don't always push in the same direction. Sometimes they reinforce one another. Sometimes they cancel out, which is exactly why it's so hard to single out one dominant mechanism and blame it for any particular wave event. It helps to keep three things separate here: what's actually confirmed by decades of observation, what climate models show under different warming scenarios, and what remains a hypothesis still waiting to be tested. Where the literature genuinely disagrees, the honest move is to say so, rather than smoothing it into a tidier story. At the same time, it would be just as wrong to say scientists simply don't know anything here. We already know a great deal. Arctic amplification itself is confirmed. The equatorward shift in the Atlantic jet's main axis is confirmed, and the mechanisms behind blocking and its link to persistent weather have been studied in real depth. What remains open is narrower and more specific: whether the flow is becoming systematically wavier because of ice loss, and if so, by how much. It's also worth resisting the urge to reduce the whole story of climate change and circulation down to the Arctic alone. Warming affects atmospheric circulation through a set of processes operating together: uneven warming across different latitudes and altitudes, shifts in atmospheric moisture, changes in ocean circulation, and processes in the stratosphere. The jet stream's response ends up differing by season, by region, by altitude, and by exactly which characteristic of the flow is being discussed: its speed, its position, or how wavy it becomes. There's no single, tidy formula that applies equally to all of those at once, at least not yet. That's why this film deliberately avoids phrases like "the jet stream is collapsing" or "the current is vanishing." Those don't match the physics of what's actually happening. The jet stream isn't a machine that can simply be switched off. It emerges directly from the fundamental temperature contrast between the tropics and the pole, and from the planet's rotation, and both of those conditions will remain in place under any realistic warming scenario. What today's climate projections actually concern isn't the disappearance of the current at all, but how its position, its strength, and its structure might change. And it's those changes, not the mere fact of its existence, that continue to be the subject of ongoing research. Understanding where this current sits and how it's shaped has very practical value too, for forecasting the weather days and weeks ahead. Small differences in how well we know the atmosphere's starting state can build up over time into meaningfully different outcomes for where a ridge ends up, where a trough sits, and which path the next cyclone takes. That's exactly why modern forecasting centers, including the European Center for Medium-Range Weather Forecasts, don't rely on a single forecast run. They run an entire ensemble, many slightly different simulations, each starting from slightly different initial conditions. When most of those simulations converge on a similar outcome, confidence in the forecast tends to be high. When they start to diverge noticeably from one another, that's a direct signal that uncertainty about the atmosphere's behavior over that period has grown. And that kind of divergence often shows up right when a large-scale wave is approaching a turning point, about to intensify into a stable block, or about to break down quickly. It's worth clarifying exactly how scientists actually see the jet stream, since photographing it directly the way you might photograph a river with visible banks, simply isn't possible. Its position is reconstructed from a whole range of data: wind and temperature fields, pressure measurements, satellite observations, data from radiosondes, the instrument packages carried aloft by weather balloons, measurements taken from commercial and research aircraft, and, finally, the calculations of numerical weather models that pull all of these observations together into one coherent picture. Sometimes satellite imagery shows long, elegantly curved bands of cloud that look almost like a mirror of the current far above them. Those cloud structures really do help trace the outline of fronts and large-scale atmospheric waves. But the clouds themselves aren't the jet stream. They're one of its indirect, visible consequences. A satellite isn't photographing the current directly. It's capturing what that current produces in the atmosphere beneath it. Throughout any discussion of the jet stream, it helps to keep returning to the question of scale. This current can stretch across thousands of miles, bend all the way across an entire ocean, and steer weather systems the size of half a continent. But it doesn't control every individual thunderstorm, every local downpour, every gust of wind through a particular backyard. It sets a broad frame within which local weather unfolds without dictating every last detail of it. And as tempting as it can be to describe this current in almost human terms, as though it decides, or wants, or attacks a particular region, the physics underneath those images should always stay precise. The redistribution of energy, differences in pressure, the planet's rotation, and wave dynamics. Not intention, not will. If we return to where we started, that snapshot of the North Atlantic in the middle of August 2026, it becomes clear that we're not looking at one single cause explaining everything, but several connected processes, each with its own nature. The cloud arc stretching north, and the motionless clear sky sitting under a ridge for days on end, are two faces of the same atmospheric wave. The warm Mediterranean is a different story. The ocean stores and releases heat on a far slower clock than the current above it changes. And although the atmosphere and the sea are constantly exchanging energy, that unusually warm water is the product of several processes acting together, not simply a trace left behind by one wave configuration. But all of these pictures belong to one larger system, an invisible current running 7 miles above our heads, and an ocean beneath it, responding slowly to everything happening far overhead. Let's widen the frame one more time, from a single region to the North Atlantic. From the North Atlantic to the entire Northern Hemisphere, wrapped in a whole series of ridges and troughs, constantly shifting, constantly interacting, occasionally locking into a stable, blocking configuration. And finally, to the whole planet, spinning on its axis, unevenly warmed by the sun, generating this concentrated corridor of upper tropospheric wind, simply as a consequence of its own physics. The jet stream isn't a fixed, static structure that's either working properly or has broken down. It's a continuously changing, living part of an enormous atmospheric system. And its bends aren't an anomaly or a malfunction. They're normal, expected behavior. But the position, the amplitude, and the speed of movement of those bends can decide whether today's weather over a given region hangs on for a few more days or gives way to whatever comes next. Climate change really is altering the backdrop this whole system operates against, through the warming of the atmosphere, through shifting temperature contrasts, through the ocean, and through the stratosphere. But exactly how each individual feature of the jet stream will respond to further warming turns out to be more complicated than the tidy, convenient formula about a warming Arctic and an inevitably wavier current. Some of the connections in this picture are already well established. Others have strong scientific support without having become a final consensus. And others remain the subject of active research, and probably will for years to come. Down here at the surface, we feel the heat on our skin, hear rain against a rooftop, notice a sudden gust of wind or an unexpected cool night. But a few miles above us, invisible and unfelt, that current keeps moving. A current that existed here long before any of us and will still be moving long after. And sometimes, how sharply that invisible current bends this week decides the simplest human question of all: whether today's weather moves on tomorrow or stays a few days longer.